Okay, in this video, we're going to look at the answers to the first exercise in Chapter 12. All right, so here's question 1. We're going to take the following 6 compounds and rank them in terms of their relative degree of activation. In other words, how reactive are they in electrophilic aromatic substitution? For example, which one of these is the most reactive to nitric acid and sulfuric acid to make a nitroaromatic, and which one is the least? Okay, so let's examine what we have on these molecules here. All right, here. Okay, if we look here, let's see, I need to set this up to have a pin function, sorry. Okay, so here we have an electron donating group. Here we have 2 electron donating groups. And here we also have 2 electron donating groups. Here we have an electron withdrawing group, 2 electron withdrawing groups, 2 electron withdrawing groups, and a single electron withdrawing group. Okay, so we know that one of these 2 right here, either this one or this one, is going to be number 1, and one of these 2 here that has the 2 electron withdrawing groups, that's going to be number 6. Okay, so how do we choose number 1? Okay, let's look at, they have the methoxy group in common. But this group is strongly activating, and this one is only moderately activating, okay? So we're going to choose this one as number 1. This one is number 2. This one with a single electron donating group is number 3. Okay, here we're going to choose this one as number 4. But remember that halogens are only weakly electron withdrawing groups. Okay, so this is number 4. So the halogen is a weak electron withdrawing group, and the cyanide is a stronger electron withdrawing group. These 2 here both have the carboxylic acid, which is a moderate electron withdrawing group, in common. Okay, so we're going to choose this one as number 4, this one as number 5, because this fluorine is not as strongly electron withdrawing as cyanide, which is going to be number 6. All right, so here are the answers. And if we look at who's activated, who's not, the 3 on the left side of this chart are all activated. They have electron donating groups on them, and the 3 on the right are all deactivated. They have electron withdrawing groups. Okay, all right, let's look at our next question here. Write all the resonance forms for the reactive intermediate in the following reaction. And this is the intermediate of a sulfonation reaction. Okay, it's important to note also, this is a bond line diagram. And don't be confused by the fact that we have hydrogens here. Don't let that make you come up with the wrong answer. Okay, so this is just a classic example of electrophilic aromatic substitution. And recall that this is where it's going to be going, and this is a electron donating group, and this is an electron withdrawing group, so this is going to be our boss or controlling group. Okay, so we're going to add right here to the para position. This is actually the attacking electrophile in sulfonation. This is what you get when you treat sulfur trioxide with sulfuric acid. It generates this intermediate right here. Okay, so the immediate product of these arrows is the carbocation that you see right here. Okay, and let's see, I'm trying to find the cursor. Where did it go? There it is. Okay. And because this is allylic, means it has its resonance stabilized. So we can draw one or more resonance structures for this one. Okay, so let's just move the double bond like that. All right, this gives us the next resonance form. Moving it again, like this. Remember, there's a hydrogen here. Gives us the resonance form immediately to the right. And there's a third resonance form that we can write as well, and that involves taking this electron lone pair. Okay, we don't have that one anymore, and donating it to the carbocation, and this is this fourth resonance structure here. This is the only one that has complete octets for all the non-hydrogen atoms. And this is generally regarded as the one that's the most stable. Most stable is not really the right term when you're talking about the resonance. This is the most representative. Okay, so remember, in resonance it's going to be a hybrid of all four of these resonance forms, but this would be the greatest contributor right here. Okay, so these are the four essential resonance forms that we have to write for this problem. Okay, let's predict the major products of each reaction. What we want to identify in each case is which is the controlling group and what type of director is that, an ortho, para, or is it a meta director? Okay, so the first one has nothing on it except a halogen. Okay, so this is a electron withdrawing group, but ortho-para director. It's actually a weakly electron withdrawing group. So this is the only group on here, so of course it's going to control the orientation of anything new, and anything new is going to want to go ortho or para to fluorine. So the answer here would be these two compounds that you see here, either para-nitro or ortho-nitrofluorobenzene. Okay, in this next one, this is a strongly electron donating group, and this is a weakly electron donating group. So this is going to be our boss or controlling group. So we're going to want to add ortho or para to this group right here. We can't add para because something's already here, this methyl group, so it's blocked. So this is the only place that it can go. And the product of this reaction, fuming sulfuric acid, is a sulfonic acid. So this is the product of that reaction, the ortho sulfonic acid that you see here. All right, in this next one, we have electron donating group, an electron withdrawing group. This is going to be our boss group. It's going to control everything. Ideally, we would like to add ortho or para to the hydroxy group. These two positions are good candidates, but it's not going to add here because this is between two meta groups. And this is not as good due to sterics, okay? It's a little bit harder for that group to come in between two meta groups. So it only do that when that's the only place available to it. Okay, so we're going to get two products here. The bromine that is added by this reagent is going to go either ortho or para to the hydroxy group. and not to the position between the OH and cyanide groups. Okay? And this next one, this is an intramolecular Friedel-Crafts reaction. Don't be confused by the fact that it's intramolecular. These are the only positions we could access here, because this is making a 6-membered ring, and if we put it over here, well, it would be meta to the oxygen. This is our strongest electron donating group. We're not going to want to add here, though. This is between two meta groups. Okay, so we don't want to add there. This is the only place we're going to see the addition right here. All right, so the product that we're going to see is this ketone that you see right here. Okay? All right, let's look at the next one. The next one has 2 rings in it. And we want to consider which is the most activated and where does it want to add within that ring. Okay, let me find the cursor. There it is. All right, so this ring here is activated. It has a OR group. The oxygen is directly on the ring. This ring here has a C double bond O on it, and it's deactivated. Okay, our reaction is going to occur in this ring right here. This is the Friedel-Crafts acylation, so we're going to add this unit onto the ring. This group here is an ortho-para director. So we're going to add ortho or para to that group right there. Okay, so our 2 products are these 2 products right here, where we have the acylation, either ortho or para to the oxygen group. Okay, so this one is ortho, and this one right here is para. Okay, this one we have 3 groups. We have electron withdrawing group, weakly electron withdrawing group, and an electron donating group. Therefore, this one is going to be our boss group. We're going to want to add ortho or para to this methyl. There's ortho, para, we're not going to add there because something's already there. And this other ortho position, we're not going to add there either because the chlorine's already there. So this reagent here, nitric acid, sulfuric acid, puts a nitro group in. And the nitro, of course, is going to go ortho to the methyl group. That's the only place it can go. All right, this next one is an alternate way to start the Friedel-Crafts reaction. Remember that anything that generates a carbocation can potentially start a Friedel-Crafts reaction. So the combination of H plus and an alkene of this type can in fact generate a tertiary carbocation. All right, so what we can do here is we can add this unit to the most favorable places in this molecule. Okay, so here we have 2 groups. They're equal, but they're cooperating because they're in a meta orientation. So everything wants to go ortho or para to a methyl group. That's this position and this position, but this position here is less likely because it's between 2 meta substituents, so that's sterically less accessible. Okay, so we're going to see not T-butyl, but the analog of T-butyl with 1 extra carbon adding to those positions in this compound. Okay, so there we go. This is the expected product. Okay, in this next one, we have 2 rings again, and this one is activated because it has an electron donating group, and this one is deactivated because it has an electron withdrawing group. So we're going to see the reaction occur in the ring that I just circled here, of the two groups, OMe and all of this phenyl stuff here, this is the stronger electron donating group, or our boss group. So we're going to want to go ortho or para to that group. Okay, I lost the cursor. It's here somewhere. Okay, all right. Those two positions are equivalent by symmetry. So we're going to put a nitro group at one of those positions, and this is the expected product of that reaction. Okay, and the final two, this is just shows the effect of ordering of reactions. Okay, so we have two steps in this one. Okay, so let's look at what we have here. In the first step, this is electron donating group. This is an electron withdrawing group. So we're going to want to put our first reagent here, bromine, ortho or para to here. And ortho is the only place. Para, we can't put anything there because the fluorine's already there. So in step one, we're going to make this compound. Okay? All right. In step two, we're going to oxidize the ethyl group to a benzoic acid derivative. And our final product has bromine ortho to the carboxylic acid. In the next reaction, we're going to oxidize it first, okay? And so this is the compound right here where bromine is going to be added, okay? All right, so when we look at this one, this is a weakly electron donating group, and this is electron withdrawing group, and this is a strongly electron withdrawing group. Thus, we're going to add where fluorine wants this to go, and it wants it to go ortho or para to fluorine. So it's going to go ortho. It's not going to go para because the carboxylic acid is already there. And when this reaction is done, we're expecting bromine, in this case, to be ortho to fluorine and not ortho to carboxylic acid. Okay, so the next video we'll look at the second exercise.